What is the specific problem that the proposed method aims to solve based on the paper?
The specific problem that the proposed method aims to solve based on the paper is to bypass the constraints of vision encoders and integrate perception and reasoning capabilities into a single unified architecture for vision language models, VLMs. The paper introduces an encoder-free vision language model, EVE, that eliminates the need for deep pre-trained vision encoders, allowing for efficient processing of high-resolution images with arbitrary aspect ratios. By developing a decoder-only VLM, EVE addresses issues such as image distortion, fragmented connections between image slices, and high computational burden associated with existing encoder-based VLMs. The goal is to achieve impressive performance on vision language benchmarks, surpassing encoder-free counterparts like Fuyu-8b and even matching or outperforming encoder-based VLMs like LLAVA1.5, while also providing a transparent, efficient, and practical route for future VLM research. The method focuses on enhancing visual perception, cognition, and alignment between vision and language modalities, ultimately aiming to bridge the gap between LLMs and VLMs by leveraging innovative training strategies and publicly available data.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method, EVE, works by first initializing a decoder-only architecture based on Vicuña 7b to establish a foundation of linguistic knowledge and instruction following ability. Then, a lightweight patch embedding layer efficiently encodes image and text inputs into the network, followed by aligning patch features with pairwise ones from a vision encoder through a hierarchical patch aligning layer. This alignment process integrates intermediate features across layers from both EVE and the vision encoder to establish a shared space for visual and linguistic information. The training procedure consists of 3 stages: LLM-guided pre-training, generative pre-training, and supervised fine-tuning, where EVE is trained with publicly available image data captioned by existing VLMs, diverse QA data, and multimodality dialogue datasets. The training settings involve controlling complexity by limiting image resolutions, using ClipVit L14 as the visual encoder, and implementing the AtomW optimizer with warm-up strategy and cosine scheduler. The model is trained with increasing amounts of data to improve performance, with a focus on aligning vision and language modalities efficiently. The ablation studies validate the effectiveness of the patch embedding and aligning layers, showing that visual supervision through PAL enhances fine-grained image representations and accelerates model convergence. Overall, EVE's architecture and training strategy prioritize aligning vision and language modalities to achieve competitive performance with encoder-based VLMs while bypassing the constraints of vision encoders.
What are the theoretical or practical benefits of using this method according to the paper?
The theoretical and practical benefits of using the method proposed in the paper include 1. Efficient integration of vision and language. The method allows for the seamless integration of visual and linguistic information into a unified architecture, bypassing the constraints of traditional encoder-based vision language models, VLMs. This integration enhances visual perception and cognition capabilities in tasks such as visual question answering and image captioning. 2. Improved model performance. The proposed method demonstrates superior performance across various vision language benchmarks compared to encoder-free counterparts like Fuyu-8b. By efficiently aligning patch features and leveraging vision encoders' output, the model achieves impressive results without relying on complex image encoders. 3. Scalability and resource efficiency. The method enables the development of scalable and efficient training strategies for encoder-free multimodality models. By utilizing publicly available data and a decoder-only architecture, the model achieves competitive performance while requiring fewer training data and device resources. 4. Enhanced image recognition. The method enhances fine-grained visual recognition capabilities, particularly for high-resolution images with arbitrary aspect ratios. By transmitting visual signals almost losslessly and aligning patch features with text labels, the model autonomously acquires necessary visual information for comprehensive perception and cognition. 5. Practical deployment and lower latency. By eliminating the need for deep pre-trained vision encoders, the proposed method accelerates the image encoding process, leading to lower latency and more efficient deployment. This results in a more responsive and resource-efficient system, making it superior for practical applications. 6. Potential for future research. The method opens up promising avenues for addressing challenges associated with encoder-based VLMs, such as input constraints, inefficient deployment, and capacity trade-offs between vision and language models. It also inspires further research in integrating additional modalities like audio, video, and thermal data into the unified architecture. In conclusion, the method outlined in the paper offers theoretical advancements in model architecture and training strategies, leading to practical benefits such as improved model performance, scalability, resource efficiency, enhanced image recognition, and efficient deployment in real-world applications.
How is the method validated or tested in the paper?
The method in the paper is validated through a series of evaluations on various public visual language benchmarks, including academic task-oriented benchmarks like VQA-V2, GQA, VizWiz, and Text VQA, hallucination benchmarks such as POPE, open-world multimodal understanding benchmarks like ME, MMBench, SeedBench, and UMVet, and scientific problem benchmarks like Science QA-IMG. The results show that EVE outperforms the encoder-free counterpart FUU-8B across different benchmarks, showcasing superior performance despite its smaller size. Additionally, EVE HD competes well with encoder-based VLMs like InternVL-Chat, MPLUG-OWL2, LVIS4V, Shared GPT-4 and Monkey, without the need for additional visual encoders for complex image encoding. The method's efficiency in deployment and lower latency is also demonstrated through inference metrics, highlighting significant speed improvements and reduced inference delay compared to encoder-based VLMs. Ablation studies are conducted to validate the effectiveness of the proposed patch embedding and aligning layers, showing that visual supervision through PAL enhances fine-grained image representations and accelerates model convergence. The paper also discusses limitations and future directions for further improving the method's performance and exploring the integration of additional modalities.
What results were achieved with this new method based on the paper?
The new method presented in the paper, called EVE, achieved impressive results in the field of vision language models, VLMs. EVE, an encoder-free VLM, outperformed the encoder-free counterpart FUU-8B across various vision language benchmarks, showcasing superior performance despite its smaller size. By incorporating diverse supervised fine-tuning datasets and larger image sizes in EVE HD, the model significantly enhanced its image recognition capabilities. EVE HD demonstrated competitive performance when compared to encoder-based VLMs, such as InternVL-Chat, MPLUG-OWL2, LVIS4V, Shared GPT-4 and Monkey, without the need for additional visual encoders for complex image encoding. Notably, EVE HD even outperformed several VLMs like InstructBlip, IDEFICS9B, and QuenVL-Chat, and performed on par with the well-regarded LLAVA1. 5. Despite facing challenges in accurately responding to specific instructions and questions, EVE showed promising potential in developing scalable and efficient training strategies for encoder-free multimodality models. The results suggest that with appropriate training strategies and high-quality image-text data, encoder-free VLMs like EVE can efficiently achieve performance on par with or even surpass that of encoder-based VLMs, offering a transparent, efficient, and practical route for future VLM research.
What are the limitations or drawbacks of the method highlighted in the paper?
The limitations or drawbacks of the method highlighted in the paper include 1. Performance gap with state-of-the-art encoder-based VLMs. despite promising results, EVE still exhibits a performance gap compared to state-of-the-art encoder-based VLMs. This suggests that further improvements are needed to match the performance levels of these models. 2. Catastrophic forgetting of linguistic knowledge. Training solely with vision language data leads to a reduction in language capability, indicating a phenomenon known as catastrophic forgetting within the large language model (LLM) component of EVE. This implies that there is a risk of losing linguistic knowledge while focusing on improving multimodal performance. 3. Requirement for larger training samples. Encoder-Free VLMs like EVE can rival encoder-based VLMs but require larger training samples to achieve comparable performance levels. This indicates a dependency on extensive data for training, which may pose challenges in scenarios where data availability is limited. 4. Potential language competency issues. The paper mentions that training solely with vision language data can diminish the language competency of EVE, as evidenced by a drop in performance on specific language tasks. This highlights a need to balance training data to maintain linguistic proficiency while enhancing multimodal capabilities. 5. Scalability concerns. While EVE shows promise in matching or surpassing encoder-based VLMs with larger capacities and training data, there is a question about how well the method would perform under similar LLM capacity and training data conditions. This raises concerns about the scalability of the approach in different scenarios. 6. Integration of additional modalities. The paper hints at the potential integration of additional modalities beyond vision and language, such as audio, video, thermal, and depth data. This expansion could introduce complexities in pre-aligning modalities and require careful consideration to ensure effective model training and performance. Overall, these limitations underscore the need for further research and optimization to address challenges related to performance parity with state-of-the-art models, maintaining linguistic proficiency, scalability under varying conditions, and the integration of multiple modalities in the encoder-free VLM framework.